Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to talk about this circuit. In order to both transistors M1 and M2 work in a saturation and are just the same, we have to determine the minimum value for W over L. But before we get started, if you're new here, please give me a thumbs up, hit that subscribe button and also the notification bell. So let's jump into it. In the circuit, as you can see, this is a circuit, and here are some assumptions, and here are the options for W over L for these transistors in order to work in saturation. So without much further, let's jump into solution. First of all, in order for these two transistors work in a saturation, we have to be careful about two conditions. Gate source voltage has to be greater than threshold voltage, and another one is that gate drain voltage has to be less than threshold voltage. We have to be careful and consider these conditions. As the problem said, M1 and M2 are just the same. It means that W over L, drain current, VGS, all of them are just the same for these transistors. So we can say that gate source 1 equals to gate source 2. First, I'm going to calculate this gate source 2 of this transistor. And let's just, for the sake of simplicity, call this node Vx. So gate source 2 equals to this voltage, which is 0.9, minus that voltage, Vx. So we can calculate Vx as 0.9 minus V gate source 2. This is Vx. Now I'm going to calculate VGS with respect to W over L, which is something that we're looking forward to it. We're looking for W over L minimum. Okay, so I have this drain current for both of these transistors. This is 1 milliamp and this is 1 milliamp, because this is a gate and gate is equals to 0. So all of 1 milliamp get through this both transistors. So I drain 1 and I drain 2 equals to 1 milliamp. Now I can write a relationship with gate source 1. VGS1 equals to square root of 2I drain 1 divided by mu and C oxide W over L plus threshold voltage. So it equals to square root of 2 times 1 milliamp, which is 2, divided by mu and C oxide. I'm going to convert mu and C oxide from microampere per volt square to milliamp per volt square. So I'm going to use 0.4. This is milliamp, but this one milli are crossed out. This is milliamp. This is milliamp per volt squared times W over L, which is something that we're looking for it actually. W over L. Okay. Plus threshold voltage, which was 0.4. So this milliamp and milliamp are crossed out, and with a little bit of mathematics you can say that this relationship is going to be square root of 5 divided by W over L plus 0.4. So this is a relationship for gate source voltage of 1 as well as gate source voltage of 2, because both of these are just the same. Now I'm going to consider the gate drain voltage. Actually, there's saturation condition for M1 and M2 separately. For M1, gate drain 1 had to be less than threshold voltage. I'm going to write some equations to identify the boundary for gate source voltage, and from that I can get the result for W over L. So first, my first purpose is to get some minimum and maximum values for gate source voltage. So gate drain 1. Gate drain 1, this is the gate 1. Gate 1 actually equals to gate source 1 minus the drain voltage. What is the drain voltage? This is drain voltage, which is Vx. Had to be less than 0.4. And I'm already had the formula for Vx with respect to gate source voltage. And as you all know, gate source 2 and 1 are just the same. So I can here substitute Vx in there, 0.9 minus, and instead of gate source 2, I can just set gate source 1 because these are just the same. Are just the same, okay? No problem with that. Less than 0.4. So if I just simplify this minus and minus 2, we have 2 with gate source 1 minus 0.9. If this one goes to the right hand side, it becomes plus 0.9 plus 0.4, which is equals to 1.3 on the right hand side. So gate source 1 had to be less than, I think, 0.65 volt. This is the first condition for gate source 1. Okay, let's call this something like this. Now I'm gonna have to check this condition for M2 transistor. M2, gate drain 2 had to be less than the threshold voltage. Now what is the gate for M2? Gate for M2 is actually 0.9 minus, what is the drain voltage? This is the drain voltage for M2, and as you can see, this drain voltage equals to gate source voltage of 1 minus gate source 1 had to be less than 0.4. So with a little bit of mathematics, gate source 1 is going to be greater than 0.9 minus 0.4, which is equals to 0.5. Consider that I actually move this gate source to the right hand side and move 0.4 to the left hand side, and because of that the sign for both of these are actually changed. So this is the condition. For example, for I'm gonna like something like this, and from both of these we can set that from this plus sign and this sign, star sign, something like this, we can set that the gate source voltage is between 0.5 and less than 0.65. Now I can substitute the relationship for VGS with respect to W over L in order to set the boundaries for W over L. Okay, here we have 0.5 less than square root of 5 divided by W over L plus 0.4 less than 0.65. Now let's move on to the next page, and again we have 0.5 less than square root of 5 divided by W over L plus 0.4 less than 0.65. Now we can calculate with some little bit mathematics. Because of this 0.4, I'm gonna add minus 0.4 for all of these numbers. So 0.5 minus 0.4, 0.1. Here we have 5 divided by W over L less than, here we have 0.25. Now because of this square root, I'm gonna take all of sides of these equations to the power of 2. So here it becomes 1 divided by 100. This is 5 divided by W over L, and this is 1 divided by 4 to the power of 2 is 1 divided by 16. Now division by 5 to get rid of this 5 in here. We have 1 divided by 500 less than 1 divided by W over L less than 1 divided by 16 times 5, which is 80. And in order to simplify this, you have to reverse it, but at the same time you have to change the sign of this inequality. So W over L had to be greater than 80 and less than 500. And as a result, W over L minimum, which is the response that we're looking for, equals 80. And with this WL over L, we can guarantee that both of these transistors on this circuit work in a saturation region. This is some kind of a design problem that we process it and get the result for that. And we can say that the option 3 is the right answer. I hope you liked this video. If that's the case, please give me a thumbs up and share this video with your friend. See you on the next videos. Thanks for watching.